Okay, good morning, everyone. My name is Roger Woods from Queen's University, Belfast. I'm a professor of digital systems, but also chief scientist of Analytics Engines, a university spin-off company. This morning's event is looking at implementing AI, and we've brought together a number of speakers. And as I say, we've just gone through the housekeeping aspects. So the plan is that everybody will be muted. You will ask questions on Q&A, and you can use the chat to indicate if you have any problems, and we have a number of staff behind the scenes. So before I give you details of the outline of this morning's session, I just want to say a few words with regard to the overall objective of the meeting. As you may be aware, our intention was to have a face-to-face meeting in Belfast at the end of March, but unfortunately events overtook us in regard to that ambition. However, we felt there was a strong need to have such an event, so we've tried to do the next best thing in terms of having a webinar and an interactive session. And as much as possible, we've tried to organize things in the agenda that we would want to have achieved on the day. So what would you have wanted to get from a face-to-face meeting? Well, you would have wanted to hear interesting and leading edge presentations. You would want to get an appreciation of what state of the art is. You would also maybe wanted to have contributed on the day in terms of your own opinion of what the challenges are. You would also wanted to have conversations and have one-to-one meetings with people over tea and coffee. So in that regard, we've put together an agenda which we think meets most of the criteria. And in some cases, the online meeting has provided benefits. For example, you don't have to travel to today's meeting. So to this morning's agenda, we will hear from 4 speakers, 2 from industry and 2 from academia about state-of-the-art work. You will then have an opportunity to ask questions both during the presentation and at a Q&A session at the end. So to do so, use the Q&A feature in Zoom to ask your questions. Everyone will be able to see that, and we've asked the speakers when they're not speaking to address the questions during the presentation. Again, this is another feature you would not have had in a face-to-face meeting. So if there's specific questions like what technology did you use, then these can be answered online by the speakers. But if there's a question such as what are the main challenges of using this specific technology, or how do you program it, I think that's an ideal question for a Q&A because everybody would want to hear the opinions of all our speakers. So we'll have the Q&A at the end, as we'll see in the agenda. So we'll be monitoring this with the aim of questions. In the afternoon, for those that have registered, we'll be using Mural to facilitate the interaction. We'll talk a little bit about this later, but it's basically a software package that allows people to actively contribute to the discussion. Then after that, we've set up meetings in Mojo, which I know that quite a few people have registered for. So in that sense, I think you'll be able to get quite a bit from today's meeting. So let's have a look at the agenda for today. Well, before that, I simply want to say the various organizations, obviously, you know, Innovate UK and their goals of what they're doing, but I'm leading the eFutures initiative, which is a EPSRC initiative to look at strengthening and supporting a network of people working in electronic systems across the UK. And really what we're trying to do is link academics to industry, but we're also trying to map out what the academic and industry research agenda should be. So we're trying to do that with a lot of meetings. We're also trying to be multidisciplinary and multi-university. So we're looking to get universities to work together and to work with both companies and interested parties from different areas of academic research. We have a monthly magazine, we have a network that we're developing to develop the strategy, and we're also looking to organize a number of different events in terms of big ideas. So again, any ideas you would have in this area are welcomed. So we have a Twitter account and also an emailing list, so please have a look at that. So if we want to have a look at today's agenda, we're going to get started in that regard. So what can I say about today's topics? Well, we all know that the previous Prime Minister has highlighted AI as a core technology for the UK. And given the UK's history both in industry and academia, in terms of processor design, we're in a very strong position to exploit this and undertake some interesting work in this area. So to this end, Innovate UK and eFutures have put together a webinar series to discuss this. And we'll have the next in the series sometime next month, and we'll announce that next week. So we've brought together a number of speakers that we can see from today's agenda. But before I introduce the first speaker, it's normally appropriate to thank people at the end. But I want to do this because it's a virtual event and some people may drop off. So I'd like to thank the Innovate UK staff, Nigel and other colleagues who you'll meet during today's presentation for all the work they've done to put this together. However, in particular, I'd like to thank Neelan Banks from Innovate UK and my eFutures colleague from Belfast, Beth McAvoy, who've done an enormous amount of work behind the scenes putting this together. I'd also like to highlight Natasha Sim from Innovate UK, who's helped us quite a bit with the software, and also James Coombs O'Brien and Liam Boyle from EPSRC for their involvement both today and during this meeting, and of course our speakers. So at this stage, I'd like to hand over to our first speaker, who is Themis Prodormakis, who is the Director of the Centre of Electronics Frontiers at the University of Southampton and founder of the spin-off company Sonnet.ai. So over to you, Themis.
Thank you so much. Roger is really, and Nigel, and of course the eFutures and the KTN team. It's really great to be here today and be able to talk about some of the technologies that we develop at Southampton. I'll try to see if I can get control of the slides. Yes, I do have that. So today I'll be talking about memristive technologies and speak about functional oxides and how these functional oxides can actually allow us to embed AI on a chip. Most of the technologies that I'll be talking today have been developed here in this beautiful building, which is the Zeppelin Institute for Photonics and Nanoelectronics, that encompasses an industrial scale nanofabrication manufacturing center where we develop these technologies. So let me see. Okay, this is the outline of the talk. So very briefly, we'll go through what are the current challenges that we're facing in terms of AI hardware, and move on to memristive technologies and what these actually bring on the landscape. And I'll try to finish by showing a couple of application examples beyond memory applications that highlight what the niche opportunities are. So our AI is really as good as our access to data. Most of you have probably seen this graph, and we've already exceeded the 50 billion mark. So we have over 50 billion interconnected devices by now that create a deluge of data. And this deluge of data has been predicted that in 5 years' time, we will be consuming at least a fifth of global electricity for simply handling the data. So everyone is appreciating that on one side, there is an energy efficiency aspect that we need to attend to, but at the same time, in order for developing more efficient AI hardware accelerators, we need to deal with the engineering challenge, which is nothing more than going from the non-von Neumann to the non-von Neumann computing era, which is bring the memory and the processing computation at the same physical location. An extra challenge that we're facing with modern hardware is that we've been relying obviously on Moore's scaling law for getting more computation and more transistors per unit area, but it's been acknowledged at least a year ago by global foundries, and a few other foundries are following, that we really hit the bottom of the scaling trend. So let's talk about memristive technologies and what this can actually bring to the play. First of all, what memristor stands for? It stands short for memory resistor. And the whole story started about 40 years ago when the chap on the left-hand side, Leon Chua, who was a professor, and he's still a professor at UC Berkeley, coined up the term memristor to describe a component that essentially is linking charge with flux. This was all done from a theory symmetry perspective, in a similar way that, for example, we have resistors linking voltage with current, etc. What really picked up a lot of interest, the point that it picked up a lot of interest in this area was about 10 years ago in 2008, when Stanley Williams on the right-hand side from Hewlett-Packard managed to correlate the characteristics that Leon was predicting 40 years ago through measurements that he was doing in titanium oxide metal insulator metal devices like the one shown in this particular snapshot. And these characteristics are nothing more than these pinch hysteresis loops in the current voltage domain, which show that there is inertia in the system and therefore memory. This is how the devices that we fabricate at Southampton look like. They are highly scalable. So for example, on the left-hand side, you could see this carpet type of image, which depicts a fabricated crossbar array in our clean rooms. And the dimensions about 1 by 1 micrometers. And in there, you have about 1,024 elements, a 1K array. Nowadays, I think last year was the state of art in terms of scaling was reported by Amherst Group, showing single devices that are down to 2 by 2 nanometers, so well beyond the CMOS scaling. But what these technologies actually bring into the mix is that you can achieve more with less. So less, I've already spoke about the chip area that is required, but is also less energy, because by going from one state to the other, you only require picojoules of energy. And what I'm showing here is that you can achieve more computation capacity. So you can store, we've demonstrated up to 7 bits of discernible memory states. And you can see in this particular graph that you actually have non-volatile, very good non-volatile characteristics over 8 hours retention characteristics from these states, which allow you to use these devices as streaming elements, essentially, as shown in the top right corner of this slide, where you can send a number of pulses for setting your conductance, resistance at distinct levels. And you can do that by simply relying on picojoules of energy. So that's where the more for less essentially approach comes from. So what can we do with these devices? What can we do with these technologies? Well, clearly, everyone is interested and excited about the prospects these new technologies bring in memory applications. But today I will be focusing on some beyond memory applications which will be relevant to the topic we're covering today, AI hardware. So first example that we've demonstrated through my group was how we can actually implement some advanced machine learning concepts in silico. And the whole idea starts by simply looking at what a chemical synapse does, which has been known for transcribing memory into biological systems. And that's the reason why Eric Kandel got the Nobel Prize in Physiology back in 2000. And if you look at a synapse, a cross-section of a synapse, essentially you have 2 terminals, a presynaptic and a postsynaptic terminal, which are separated by a synaptic cleft, and you have the diffuse of neurotransmitters. Well, in a very abstract analogy, in a way, as an engineer, if you take a cross-section of one of our memory store devices, you would see that there is quite a bit of similarity there. You have, again, 2 terminals. The blue areas are platinum electrodes. So you have a top electrode and a bottom electrode. And still you have, instead of a synaptic cleft, you have an insulating medium in between, a barrier in which different species are mobilized to transcribe memory. In this particular case, this is titanium oxide, and you are able to move titanium interstitials as well as oxygen vacancies up and down. So with that abstract analogy, you have a very compact and very efficient way to emulate synapses and synaptic weights. And if you start stimulating these devices with positive and negative pulses, as you could see in this figure here, shown in red, you can then register some analog weights into your memoristic devices. So you have these nice analog waves that show the modulation of your resistive state. And this happens, there is a sort of two thresholds, a positive and a negative switching threshold, above which all the magic happens. And in between, no change in the resistance is registered. So if you take that and you have an appropriate learning rule, that allows you to potentiate and depress your devices, or actually have no activity at all. And one extra attribute of these devices, which is particularly useful for neuromorphic systems, and in this particular example, is the history dependence. So depending on every state modulation depends on the history of the device, on the previous state that the device has actually stored. So for example, if you are in a relatively high conductance and you want to push your device towards a lower conductance, that's relatively easier to happen as if you were to do the other way around. So going from a high conductance to an even higher conductance, which is essentially quite similar to what electrophysiologists see. Strong synapses have a tendency to in a more easier way become weaker, and vice versa. So if you take these devices, you can then start developing simple neuronal networks like the one shown on the left-hand side, which is a winner-take-all configuration. And in this particular case, we've actually demonstrated how you can implement unsupervised learning with probabilistic neurons that also allows you to handle mistakes and errors in the incoming signals quite well. The beauty of this approach is that no prior training is actually required, since you don't necessarily know what the incoming signals are, and the system is able to classify and to identify the different class centers of your data as these drift over time. That's particularly important for embedded type of applications, and you could say that not only the system learns, but it can actually forget and relearn new sort of data class centers as they come in and as they drift over time. So that was one example of what we can do with these memoristic technologies. A second example has to do with how we implement energy efficient, how we achieve energy efficient Bayesian inference, which is a topic that a lot of people have an interest in. And one of the core, if you like, operations that one needs to do in such cases is multiplication. However, multiplication is one of the operations that is quite costly in terms of implementing this in silico and in hardware. And what we've demonstrated in this work is that you can simply take passive crossbar arrays of these memoristic technologies, and that would allow you to do vector matrix, vector multiplications, and so forth, by simply exploiting Kirchhoff's law that would allow you to add currents in these rows. A third example has to do with alternative paradigms for computation. And on one side, we do know that our world is purely analog. We see with smell, we sense essentially with analog by using continuously analog signals. And nonetheless, our electronics, for the reasons I mentioned before, because of scaling and because of energy efficiency, has actually been dominated by digital fabrics, if you like. There is obviously the analog and the digital paradigms, which still remain separable. And there is the third paradigm, which is a mixed signal approach, but the mixing is actually done exactly as it says on the tin, at signal level. The underpinning technologies still remain separable, which means that you still have the same issues in terms of sending data back and forth, which causes latencies and which in turn causes additional energy expenditure. So if we want to move really forward, we really need to see of alternative design paradigms. And this is one example. If you take a standard inverter, that's the very much well-known transfer characteristic of an inverter. But what will happen if you were to integrate these analog memoristic devices locally here within your inverter? Essentially, what happens is you skew the characteristics, the transfer characteristics of your inverter. And what you have now is an analog gate. So you can achieve analog computation, but overall very, very similar to the cost of digital, which is quite a powerful example. And not only that, you can exploit this reconfiguration capability of these memoristic devices to set the memory states at different distinct levels, which will overall allow you to shape the transfer characteristics of your analog reconfigurable gate now. So where would this be useful? This is again just one extra example where you can have a primitive readout circuit assigned with this analog reconfigurable gate, and which could allow you to tune this particular circuit for looking at specific values within this circle shown here. So essentially, you can create in silico classifiers which are quite efficient. When you hit the target, you can get a very prompt response, but in all other occasions, your classifier essentially consumes minimum power. And not only that, at the same time, it also points to you to which way you need to move your focal point for identifying the target. And this is just a more elaborate example where you can now take this texel, we call it template pixel essentially, and tessellate it to allow you to do classification in a range of data. In this particular example, we're classifying different spiking events from acquired from electrophysiology experiments, but obviously you can scale this and apply this to a number of different classification problems and a number of different sources of data. So moving on, a fourth example has to do with how can you employ the device physics for doing some sensory data compression. So really doing signal processing at the edge, and because there is a lot of different definitions of what edge computing means. Here, literally, we mean at the edge, we mean at the device front. So if we were to look back at the operation characteristics of the devices that I've described previously, essentially you have these two threshold points where you have a soft breakdown and a hard breakdown. Ideally, you want to stay away from this hard breakdown where you have irreversible switching. But below the soft breakdown, nothing actually happens. And the magic happens somewhere in between, in this green area. So as you could see on the graph on the left bottom side of the slide, as you start pulsing your devices, the moment that with voltage pulses, the moment you exceed the switching threshold of the devices, you start modulating the resistance and you start changing the resistive state of your devices. Why is this useful in this particular case? Take the example of neural signals that have been captured by multi-transistor arrays. You have a signal that looks like that, which could be quite messy and quite complex, but it's quite rich in terms of information. But merely the information exists in the spikes of these signals. So as you could see, what we've done in this particular case is we've preamplified the signal. We used it to bias directly these devices, which allows you to align those spiking events, and some of them exceeding the switching characteristics of your devices, the threshold of your devices, which essentially would allow you to register every single spiking event as a modulation in the resistive state of your devices in a non-volatile way, which means that you can actually have passively these devices sitting there, not consuming any energy, and simply integrating all of these firing events and allow you to look at the transient response of your memristive states and figure out how much activity has been there. So do spike detection in a way. But one of the big challenges electrophysiologists actually have is that not only they're interested in knowing when activity has happened, but they're also interested in knowing what kind of activity has happened. So spike detection to spike sorting. And as you could see, there's a variety of different spiking activity events and shapes. And the beauty basically of our approach is that the change in the conductance of the device is dependent on the envelope of this spiking activity, which means that you will have a corresponding and an analogous change in the overall resistance. And overall, that can allow you to self-classify these spiking activities. Instead, so essentially do at the device level, do not just spike detection, but also spike sorting, which is an extremely computational demanding approach that is typically done by template matching and supercomputers. And of course, this approach allows you not to share your data via very specialized high bandwidth techniques like optocouplers, etc., and having it on chip and minimizing the latencies that will be particularly useful for neuroprosthetic applications. So with this particular example, we move a stage, if you like, forward. And this is something that we've demonstrated very recently and has created a lot of excitement in news media, as well as the scientific community overall, which is if you have a technology that essentially speaks the same language as the biology, you might as well use this to link to biological systems. And what we've done in this particular example, which is the outcome of a European project called RAMP that finished about a year ago, which is a collaboration with the Institute of Neuroinformatics and Padova University. So we've managed to link for the very first time real neurons to artificial neurons that were located in an integrated system chip solution in Zurich via memristive synapses, and vice versa, get the output of those artificial neurons modulated again through memristive synapses and stimulate now the real neurons sitting on the cultured medium in Padova. And this was all done over the web, which is actually quite fun because especially in this special times that we live in with the challenges imposed on us on COVID, we are still able to continue some of these experiments by working from home and doing it all remotely, which I found it quite good fun, I have to say. So what's really next? There is still a lot of work that we do in my group in taking the lessons learned from these particular technologies and the benefits from this for implementing AI on chips and developing advanced chipset solutions for compressing sensing, as I've mentioned previously, but at a larger scale, for classification, for natural language processing, as well as image classification, for advancing learning capabilities, specifically for problems that require to deal with systems that are continuously on, and effectively also come up with new hardware architectures that allow us to do reasoning by correlating uncorrelated, seemingly uncorrelated data sets. And that's essentially the remit of Sonnet AI, which is a new startup that we've developed at Southampton. So to finish off, how could really the future look like? If you obviously have these emerging classifiers that are consuming really low power and you can have them locally, it means that you don't have to share your data with the cloud, which intrinsically is a much more secure approach. And the future looks quite exciting ahead because we have opportunities that are unprecedented opportunities for applications in the area of bioelectronic medicine, replacing drug compounds with electronic devices that can close the feedback and stimulate organ function as needed. But also, as we've shown with the recent example, go and replace, if needed, any dysfunctional areas of the human brain, and perhaps, if we want to keep dreaming, perhaps even augment intelligence in a way. And as Feynman says, what I cannot create, I do not understand. So I do believe that there's a great hope into these technologies. There is still a lot of challenges with these technologies. And this is a commentary that we contributed in Nature Communications about a year ago or 2 years ago. I invite you to read this because it deals with what are the open challenges in these technologies in terms of the variability, the yield. And one of the key challenges is obviously the integration with still existing technologies, which is something that we do through an EPSRC funded program grant called FORTE, for reconfigurable technologies. This is the first actually engineering run, and we're able to do that at full 8-inch wafers collaboratively with TSMC, and we're developing a full PDK for the technology that we're hoping that we will be able to offer as a service to the rest of the UK community. So what's the space? I'd like to thank obviously our founders and the group for who's behind all of this work that I've described today. And there is quite a few opportunities if you have any colleagues or anyone who's interested in doing a PhD with us, or a research fellowship positions, as well as a lectureship that we're advertising at the moment in AI hardware. So thank you so much again, Roger and Nigel, for the opportunity to talk, and I'll be happy to take any questions.
Thank you very much, Themis. I think there's a lot of issues already being raised there with regard to how we incorporate the AI functionality. Obviously, the big issue with analog and digital is we start to see the technology causing issues. So I think there's a lot of questions there, and I would encourage you to start to populate things through Q&A. As I say, Themis is staying on for the whole of the morning to be able to answer your questions. So without any further ado, I'd like to hand over to Ian Wallace from Rovco, who's going to give us a company perspective on some of the challenges as well. Over to you, Ian.
Hi, good morning. Sorry, I'm just going to pull up the chat here just so I can see what's going on. Okay, so 2 seconds. Right. Thank you for organizing again. So yeah, as mentioned, I'm going to provide a bit of a different perspective here, talk about an application case, I guess, of embedded AI, and a bit about what we're doing at Rovco. I thought I'd start by introducing myself. I'm Ian. I'm the Chief Scientific Officer of Rovco. That means I'm in charge of our R&D and our technology development. My background is some embedded work, but mostly from an AI point of view. I've been working in AI and robotics for nearly 20 years now, starting off defense sector stuff, some human-robot interaction, some embedded sensing around indoor localization, more recently Mars rovers, tunnel inspection robots, that sort of thing, and now subsea robotics. I think, yeah, it's always nice to have a bit of an intro so you know who I am. I put my title on there, the doctor there, just to give you some impression that I know what I'm talking about. Some of you will have PhDs, just know that means I'm the world expert in something so specific no one else cares about, but it's a type of AI in this case, so it is relevant. So getting on to what I'm going to cover here, very different to the last talk, but that's the point in providing an industry perspective. I wasn't sure what the audience would be like, so I'll start by providing a bit of an overview to what is offshore robotics, because I don't know what mix we've got in terms of people interested in deeply technical content and people interested in business content, but there's probably not many people who know about offshore robotics. I'm going to talk a bit about what AI is in general and in this context, because it means different things to different people. So I'd like to set the scene there. And I think we do a lot of activities which you may or may not classify as AI. And then I'm going to finish by talking about the embedded AI challenges we have in this domain and some of our hardware and software and business solutions to them. So a little bit of everything, which is either a little bit of something for everybody or leaving everyone equally dissatisfied, you decide, but do ask questions and I can pick them up at the end in the Q&A session later. So I'll start with a bit of who Rovco are and what we do. So we're an offshore robotics company. So what does that mean? It means we go out with robots doing offshore work. There's a video playing now which will give you some example of what this looks like. And we develop the technology. So not only are we going out throwing robots in the sea to do real work, we're making these robots smart. It's an interesting industry to be applying AI to, because I tell most people I'm the CSO of a subsea robotics company. They assume the robots are the new thing. But this is a nice AI application that the robots aren't new. We've been working offshore with robotics for getting on for 30 years now. And this is an environment that is so harsh that people either very rarely are in this environment, or it's physically impossible to put people in this environment in some cases, depending on where we're working. So the robots are not new, but the traditional way of doing things is effectively remote controlled submarines getting driven around by people on boats. But that's kind of not the future, and that's what Rovco is about, technology to enable this. So you'll be seeing on screen some of our 3D technology. This is, we use camera sensors to build up live metric 3D models of the environment. This helps perform the tasks we have to do, sort of inspection tasks, maintenance tasks, and it also is a sort of this key perception piece for an AI system, understanding the world around it. And that's kind of a brief bit of what is offshore robotics. So we're going out on boats, we're doing work with robots, and we're making those robots smarter in a variety of different ways. So again, this is a whole industry which is a huge industry, but likely invisible to most people. This is what you've probably seen. Wind turbines sticking out in the sea. If you've ever flown into Amsterdam, and you'll see them in the channel as you fly over. Wind turbines are a big part of our work. It's things like oil rigs, or another obvious one. Cables for electricity and communication, pipelines, harbours, mooring chains, etc., etc. I'd say for us, the big business is renewables. More than 95% of our business is in renewable energy, and a lot of that is focused on the cables on the seabed and where they come in and out of the turbines. What I like to say is cables and pipes are how you get the money out, so that's what people really care about. So that's the kind of a working environment. Offshore wind, if I talk about typical water depths, they vary. It's typically tens of meters or low hundreds. You get floating wind turbines are starting to appear now, which can be moored in deeper water. And of course, the mooring is important to inspect. And you get oil platforms, anything up to 6,000 meters of water, you might have things. So what does an ROV look like? What are the sort of robots we're talking about here? I say typical ROV. I'm not sure there is a typical ROV. They all look broadly similar. So what I've got pictures of here is a mid-size, a small work class or mid-size observation class ROV. They typically all look, as I say, look similar, but scale up and down in size. They've got thrusters. They've got 4 degrees of freedom, so they can move forwards, backwards, left, right, up, down, and then they can rotate. They don't typically tilt themselves up and down. They don't go very fast, about 3.5 knots. Mostly that's about holding their position in current. They typically have SD or in some cases HD cameras, sonar, lights, depth sensors, etc. And they range in size from size of a coffee table up to size of a small truck. So vary quite a lot. I mean, I said 85 kilos to 1,200 kilos plus. We have some going smaller than that, and we have some that are larger than that. The processing is typically on the top side for a traditional one, sending data up either a copper or fiber optic tether. But that's a typical one. What we do is a bit untypical. The environment we're working in is a very harsh one. This is some snippets of some of our inspection video. You can see all kinds of different water conditions, all kinds of different environments, different bits of structure. It's not a nice computer vision environment, but there you go. And in terms of AI, well, it wouldn't be a talk on AI if I didn't show a video of some boxes being drawn around things on a video. This is some examples of some of the stuff we do. So here, what you're looking at is the inspection of what's called a monopile. That's a structure that holds up a wind turbine. We have these water replenishment holes to keep the water on the inside and the outside of the monopile at the same level, and they have marine growth and they get blocked up. So we need to detect that. We have anodes which corrode preferentially instead of the structure, and we need to monitor their depletion. And these are ML applications that we do. But this is just a nice sort of video example of an ML application, but that's just machine learning, and AI is much more than that, certainly in our use cases. So I always like to talk a bit when I'm presenting our work in terms of what is AI, just to kind of set the context here. So what you've got playing in the background is the visualization from our live 3D vision system. So this is obviously one of the things we do is moving around quite a large structure. You can see where visualization of where the robot is. You've got the camera view coming in, and you have this dense point cloud being built up on the side. But I normally break it down into five components, which I consider to be parts of AI or an AI system, and say we do all of them. So the first one is perception. So this is how does the robot perceive the world around it? How do you go from a visual input like we're getting in the bottom left here to some richer information? So that's kind of a key thing. The next thing I generally talk about is memory. So this kind of works hand in hand with perception. Here you're seeing a large model built up. It's more than the robot can perceive at any one time. There is some memory of what has been before and after. And this can happen in, you can apply these 5 things to many different robotic or AI use cases, not necessarily embodied in the physical world only, but that's a key thing. Then I'd say reasoning. Reasoning is a bit of a subtler point. The way I tend to describe this is reasoning is using some sets of rules and knowledge about the world, what you've perceived, what you can remember, to generate new knowledge that you cannot directly perceive. So normally if we're all in the same room, I would give a nice example of this by pointing to the door and saying, hey, you all came in that door. You know there's an elevator out there in the hallway or whatever, but you know I'm not stood in the elevator. And you know that even though you can't see the elevator because you can perceive me in front of you, and then you reason about this. So I guess a similar example on a video call is you know I'm not stood behind you wherever you're sat, because you can see me somewhere else, not because you can directly perceive that to be the case. So that's a sort of simple example of reasoning, but that's sort of most generic. In a kind of robotic inspection case, like I've got playing in the background here, you can imagine if you're inspecting all the anodes in a structure, and you see that there's an anode is somewhere it shouldn't be, then you can reason that is not where it should be without necessarily inspecting it. Planning is a fourth thing. So this can be planning in terms of motion planning. So where should I move next, right? Think about this robot building up this map of this large bit of equipment subsea, where should it move next to get a good view? And also task planning in terms of if my task is to build up a map of the structure and then inspect specific elements, you know, what order do I do the inspection and things like that. And then the last one kind of gets back to the kind of classic ML example I showed of predicting the objects in a scene. So this is prediction. So that's from noisy sensor input, predicting things about the world. I mean, there's a bit of overlap with perception there. It is estimating things like this. So there's kind of these 5 things, and I would say, you know, the classic ML, what people call AI these days, of deep learning applied to image data, say, fits in the prediction part, but there's a lot of other things that are AI. I'll not go into any more detail in this. I will say I've given talks on this whole topic before previously, so if people are interested or want to debate with me, I can point them at that. But what is all this in terms of what we do at Rovco? So this is all about, kind of a key point here is, and I'll be getting to the embedded hardware. Here's a nice render of one of our camera systems, which contains some embedded AI and compute. But it's the whole system. So you've got large vessels like these doing work. You've got a robot often on the end of a tether, but perhaps untethered for an autonomous underwater vehicle. And it's got to move around. It's got to explore the world. You've got detection of things. So if we talk about prediction and sensing, the example you're seeing here is the robot's moving along a pipeline and it's detecting objects of interest, logging them in the system. But then this enables a wider system, so we can have remote access to the same data, even though we've got very low bandwidth links or irregular bandwidth links, because the information of what you've detected and where is much lower bandwidth requirements than the raw video. So, you know, by embedding the AI in this, we get a different complete system. The same applies to this kind of perception piece. So the raw video data is very large data, but the 3D model can be represented compactly, so we can stream that remotely. So this is part of what we do as well. And why does this all kind of matter commercially as well? The large vessel that you saw at the start of this, which might be out at sea deploying the robots, that vessel, it's got about 60 people on it, but only 2 of them are maybe driving 2 robots at any one time. There's a lot more people that are there to look at the data. So if we can get this data and actionable information elsewhere, you can reduce the size of the vessel, reduce the environmental impact, reduce the cost. When I talk about cost, a large offshore survey vessel like that operating will be costing in the region of 60 to 100,000 pounds a day, and it might be out there for months at a time. So you can say it's about £1 a second to run these systems. So, you know, strong incentive to make smarter systems. So I'm talking about embedded AI here. So what does our embedded hardware look like? Here's one of our camera systems. We embed intelligence into our camera system so we can deploy them in different robots. Different tasks require the use of different robots. So yeah, it's a 4K camera. It's actually a pair of 4K cameras in there. I'll not talk a lot today about the detailed internals of that. There are some questions I'd maybe answer on it, but some of that we keep proprietary. It's a patented camera system as well. But it's about delivering 3D models. That's kind of our key thing, because the job, if you like, that people are doing is not just looking at things and seeing what's there, it's measurement and things like this. So this brings some kind of key challenges in the hardware, deploying an embedded system in this way. So they're kind of obvious ones. You're going underwater, there's high pressure, you're going down to perhaps thousands of meters. So you need to have these sealed enclosures, they need to be very thick. So then heat becomes everything, heat and power. You might say, yes, you're water cooled, but yeah, you're in this tricky enclosure that might want to be made out of steel, which is actually quite insulating. There's a huge performance burden. 4K cameras shooting, say, YUV422 video at 30 hertz is about 4.5 gigabits per second per camera. So you're talking about 10 gigabits of data. And then somehow you either need to squeeze up a pair of copper wires to the surface or a tether, or maybe there's no connection at all. And I said this costs about £1 a second to be there in some cases, in which case reliability is a big deal. So what do we do in terms of our embedded hardware? We're on NVIDIA platforms, various different Jetsons. I've got a picture of a TX2 here. And I kind of wanted to get into some technical content in this talk, so I'll talk a little bit about the art of the possible here in terms of what appeals about these. Nice little video encode block in there. I've highlighted. There's also a nice GPU there attached to the same memory. This lets us do some of our nice applications. And video quality is kind of very important to us. I mentioned this very high video bandwidth that we're dealing with. And yeah, just nice background picture here. This shows why we need quality out of our cameras. This is the touchdown point of a cable from a wind turbine going under the seabed. This isn't actually a photo. This is a view from a 3D render produced by one of our 3D models produced by our system. So what's kind of possible currently with this stuff? Well, you can't read the numbers, but I'll talk over it. This is example power data for encoding video coming on in this case, a TX2 coming off 4K camera sensor. You're looking at two spikes in the graph. The first spike there is generating some test data signals. That's our kind of baseline, just to generate the test data that we're testing with. And then the second spike is the power consumption to encode. So what you want to look at here is the green line, which is the encoder power, which is, you can see, about 1.8 watts. And what we're getting for that 1.8 watts is we are encoding 4K in HEVC codec to disk at 100 megabits a second. We are streaming a downscale 1080p stream at H.264, and then we're also rendering to the screen, and we can do all that in 1.8 watts, which is quite incredible. So that's the kind of where we are. So this is great for a really power and heat constrained system. The other thing, as well as video data, we care about is deep learning, which allows me to do a slide with a terrible pun on it. And this is I think quite interesting. If you're doing an embedded system, you'll see, for example, if you look at NVIDIA's marketing stuff, they do a lot of promotion on their speed and execution time performance, but really power is everything, because power is heat, and heat budget is the thing that defines a very tightly embedded system like we've got. So what we really care about is how many joules does it cost per image that we inference, and that's what the chart on the left shows you. And this is kind of, again, in this case, data off a TX2, but this is showing for a given amount of energy. And I chose the amount of energy in one Mars bar because that gets me nicely to 500 images on a optimized TensorRT implementation on a TX2. And then you see that same optimized implementation on a desktop class GPU only gets you less than half as many images for that amount of power budget. And then on an unoptimized deep learning implementation, you know, a third of that again. So you really can get, and you can do better than this with more modern hardware as well. And what does that mean in terms of practically our power budget we've got in the system? It's what the top right graphs are. Again, it's showing total system power, CPU power, and GPU power. The orange line is GPU power. There's a yellow line along the bottom, which is barely visible, showing we've got hardly any CPU usage, and we're under about 8 watts to do inference here, which is incredible. The bottom graph is desktop class hardware up about 140. So for 10 watts, we can encode and stream all this video and do inference, which is great. Finally, I just wanted to kind of put this in a kind of the wider context. The embedded system is part of a whole system. I showed that demo earlier, where you know, you're streaming the data from the robot up to the vessels over a low bandwidth satellite link and back to shore. And in kind of deploying an embedded system, you've got to think about a few things. So one is like, where is the bandwidth? Like if you've got very low bandwidth, you want to push the AI out to the edge because you want to send just the results back, not the raw data. But then if you're dealing with cheaper hardware, or you want to have maybe you're thinking about different industries where you've got you know, cheaper, lower power devices, you might want to push the AI back in from the edge back to the cloud. And then you've got to think about where the AI gets deployed. So, you know, can I deploy the same AI systems in the cloud as the edge? And that's a big advantage we have from the NVIDIA platforms, is we can run a lot of our code the same everywhere. I just noticed a comment in the chat about video quality. That Zoom is terrible at delivering video remotely. Sadly, you'd think it'd be better, but yeah. So my point here I'm making here is embedded is only one part of the system, and where the AI happens and where the AI is changes. So I'm going to finish with a kind of illustrative example and something for participants to maybe think about. So applying AI is a complete solution. It's not just the embedded. Consider this is one of our systems you're viewing on the left. So pipelines scrolling by, there's detections being made of objects of interest, and they're being located on a map. Now, where is the AI in this case, right? It could be multiple places. You can imagine the one deployment scenario where it's happening on the robot itself and just the results are being sent back, and then we can visualize them in the end user. It could be happening in the data center. This could be historical data, say, rather than live data, or it could be live data and we're streaming the video. Or it could be happening in the browser, right? And yet the user's experience is exactly the same. So for every user and every use case, even for the same system, is the AI always embedded? Is it in the same place? And is that always true now into the future? So, what we do now might not be the same as what we do tomorrow, depending on robots and things like this. So just kind of trying to get the viewpoint up there that I guess embedded AI is always changing as it's where it's embedded. So, yeah. Thank you everyone for your time, and I'll hand back.
Ian, thanks very much. Absolutely fascinating. And as I say, very much a state-of-the-art application. Obviously with image data, the amount of memory being used, obviously very challenging from that perspective. So I think it raises a lot of questions, and I can see from the Q&A you have a couple of things coming through. So as I say, there's probably topics there for later on. Where do you keep the image data? Do you need to keep the original content? Will that influence how we do the AI? So I think there's a lot of points that will come up on the Q&A. So at this stage now, I want to hand you over to Jose Nune Llanes, who's a reader from the Adaptive and Energy Computing at the University of Bristol. So over to you, Jose.
Hello, good morning. So yes, thank you, Roger. So as I am a reader at Bristol and also currently a Royal Society Fellow on Machine Intelligence at the Network Edge. And I'm going to present some of the work we've been doing on this topic of heterogeneous and adaptive computing for energy efficient AI. So we have this structure where initially I will discuss the energy and performance challenge of in artificial intelligence, then how companies are creating custom hardware to address this challenge, and then how we can go a step further, optimizing energy and performance using these chips and with techniques such as adaptive voltage scaling and heterogeneous circuits. Finally, I will discuss conclusions and future work. So, well, I think more or less we all agree that AI is an energy guzzler. It's extremely power hungry. In general, we all are the training phase is very compute intensive and consequently power hungry. But the idea is that, well, in theory, you only need to do it a limited number of times, and you can do it at locations with no constraints in resources like servers and so on, where you make sure that your algorithm is properly trained and performs correctly. On the other hand, inference, that is when you deploy these neural networks and AI in your applications, will be is much simpler, but need to be done continuously. So, and typically you need to do it in places where you have constraints, a constrained environment, such as near the sensors of the machines that you are monitoring for trying to find defects or trying to monitor how it's behaving. So this idea then imposes much serious constraints, and it becomes also an energy and power issue. So to address this issue, well, people could, initially we were using things like general purpose CPUs and GPUs from Intel, from NVIDIA and so on. Well, just to get one step further, companies and academia have started developing hardware accelerators, basically ASICs and so on, and other reconfigurable chips to obtain a better throughput, to obtain better energy efficiency and also low latency. And in here we have a big range of power profiles we have technologies such as Google TPUs, tensor processing units, Intel with their immediate and neural compute stick systems. Then we have the FPGA world, where we have chips also from Intel and Xilinx, and then startups such as GraphCore and so on. And in here we have power ranges in the order of watts. GraphCore has a chip with 150 watts and so on. And many of these chips are specialized either for inference, or some of them can do inference and training as well. And then on the other edge, on the other side, we have power profiles of milliwatts with embedded processors, such as, for example, Technic RISC-V with a GAP8 platform that is a multi-core with 8 small RISC cores that and also a neural network accelerator, and then techniques such as sub-threshold voltage computing deployed with startups such as Eta Compute and Ambiq, where they try to adjust the voltage and frequency to extreme levels. So in this work, we are seeing, okay, how we can combine these different chips that have many different power profiles, many different features. Some of them support certain neural network features, others other network features, and how can we deploy them, and how we can obtain energy efficient and optimal operating point of energy efficiency depending on what chip how the chips are being combined. So in here I present a case study. One of the good things of these neural network accelerators and machine learning in this field is that there is quite a common frameworks that are supported by everybody. Like if you want to enter into this field, you probably need to support things like TensorFlow for programming, because otherwise it will be very hard you come with your own framework for developing neural network algorithms. So that means that you can create heterogeneous systems where you only can train once, and then using like TensorFlow, and then using just this single output of TensorFlow, optimize it for all these chips, but without needing to retrain it. So, and this is the case what we are using in here. We are using TensorFlow, and we are targeting different chips, such as in this case, fixed-parallel gate arrays and tensor processing units. Our hardware consists of a Sync ultra-scale board, a ZCU102, that basically is a chip where we have an ARM host that is going to control everything, and an FPGA that is going to implement our accelerators. And we have added a Google Edge TPU to the system. In the Xilinx part, we have a deep learning processing unit that is a soft FPGA overlay created by Xilinx, where we can have adaptation of the architecture to the complexity and the FPGA resources. On the Google Edge TPU is an ASIC. They both are based on a systolic array as the main compute unit, and they are also both specialized for 8-bit precision, integer precision of 8 bits, that is generally seen as good enough for inference. Obviously, the big TPUs used by Google on the cloud, they have floating point, they are used for training, but here we are seeing an embedded system where we are combining this Sync ultra-scale plus the Google Edge TPU. Again, we use a single framework based on TensorFlow, and then we will freeze the network and customize it using the custom tools for each of the vendor, but we will use the same weights and so on for each of these architectures. So this just shows a picture of our Sync ultra-scale platform, where we have in here, we will have a number of peripherals. One of them is a USB 3 interface. This is where we have attached our Google Edge TPU. So the ARM host is a multi-core and is running Linux. And in there we have the drivers and so on to control the Edge TPU. And also on the FPGA side that is in here, we have implemented or created our deep learning processing unit from Xilinx. So the host is in charge of getting the video frames and scheduling operations to both TPUs and GPUs to keep them busy to obtain the most optimal operating points in terms of performance and energy. Also, the USB interface, we have seen that is not really an overhead, because the video frames that are being passed to these processing units are not that big. Normally they are like 200 by 200 pixels. So it does not constitute really an overhead that is limiting our performance. So in here we see our application benchmark. It's a popular neural network called SSD, single shot detection. So this is a neural network that will do both detection and classification of objects using a single processing step. So it's very complex. There's a lot of neural network layers going on in there. And we have done that idea of training once. Training will take several days, but then reusing everything to target both the HTPU and the DPU. If we look at how the performance is working, here we have the idle case where the system is idle, so there is no really any workload or running. Then we have here the one DPU case, the one TPU, tensor processing unit case with the edge TPU, and then both combined. The green shows performance, so obviously when it's idle, performance is 0. And then we can see that the DPU in here providing around 80 frames per second, the HTPU about 30 frames per second, and once we combine them, we obtained a good scalability of 115 frames per second. In terms of power, we see that the DPU that is running on the FPGA side is using about 5 watts. The TPU is about 1 and a bit watts, so it's more power efficient, I guess expected because it's an ASIC, it's not using the overlay of the FPGA. The performance on the DPU is a bit higher because it's using, well, it's been optimized in a different way. It's using the FPGA in a particular efficient way. Also, something we notice in this data is that most of our power is actually idle power. The activity, when the things are running, the increase in power is not so significant. So in here we can think, okay, what sort of things we can do to optimize this further? And there are techniques like clock gating, power gating that can be deployed. Of course, in the HTPU, we are a bit limited by what Google makes for us. But on the FPGA, we have access, we have low-level access to the hardware infrastructure. So in there, we can do more interesting things. And one of the things we've been working is adaptive voltage scaling. In here, in these pictures, we just see how single-shot detection is working. We see performance of TPUs and DPUs, and it's detecting objects and then telling you, it's being trained with this Berkeley deep drive system. So it's trained to detect cars, signs, typical things that will be relevant to autonomous driving. And of course, we have a lot of information of all the power rails, and because we can monitor all the power rails in parallel and see how power is being used by the device. So how we can do this better, how we can bring, for example, the power profiles in here lower. And we are trying to deploy this concept of energy proportional computing that basically will mean, well, depending on the complexity of the job you are dealing with, for example, depending on the complexity of the frames, of the number of objects in the frame, try to adjust your performance so you only deliver the performance you need to complete the task on time. So instead of running a full throttle, depending on how the inputs are taking the complexity of the inputs, we are going to adjust the system performance and obtain better energy proportionality. Something we can do on this system is control the voltage levels. So on the ZQ1 board, there is PM bus, Power Manager bus implemented. So we not only can't read the voltages, but also set the voltages. So that means that we can change the voltages so that the FPGA is working. So we have been working on this tool that we call Elongate. That basically what Elongate will do is analyze the netlist you are trying to put on the FPGA, in this case, the netlist for a deep learning processing unit, identify the timing critical paths, so basically the endpoints, the critical paths of your design, and instrument that netlist with detectors that will analyze when the critical paths are about to fail. So it consists, here we see the typical flow of Elongate. We will start with our source code that could be maybe some C code, some VHDL code, some Verilog codes. The idea is that we do initial synthesis and then we obtain a netlist, a technology netlist for the FPGA device where we will have our lookup tables, our slices, how the thing is being configured. We carry on through the map, place and route and timing analysis. And then what we do is get all the timing information that contains all the timing about where the critical paths are on the design and so on. And the netlist and use Elongate What Elongate now will do is use the timing information to find in a netlist where the critical paths are, and then we'll replace those critical endpoints, critical paths, basically the flip-flops that are typically at the end of the critical paths, with soft macro flip-flops that will be able to detect when, due to voltage levels, the critical paths are about to fail. So when timing is about to fail. The critical concept is that these in situ detectors we are inserting should detect the failure of the timing before it affects the functionality of the design. Then once we have done that, we will create a new netlist with instrumented with these detectors. We complete the place and route and bit generation, and we have a bit stream ready to put into our FPGA. So as an example, here we see an example of a timing detector for logic. So what we have here is a number of logic cells on the Xilinx Sync Ultra Scale device, basically combining lookup tables and flip-flops, plus our carry change path in here. There are basically 4 logic cells in this slice. And what we see in green is our original critical path that was ending up in this flip-flop. So this is our original path. The instrumentation, what it does is replace that logic cell with a new configuration where we control and create a new path shown in red that is slightly bigger than the original path. This goes to our SFF, that is our slow flip-flop. And then this red path is about 200 picoseconds larger than the original path. Then the output of both flip-flops will go through an XOR gate and a synchronizer to remove metastability issues. And then it will be output to a control unit that will be monitoring all these critical paths for possible timing failures. Typically, there will be a few thousands of paths we are protecting, and we are monitoring them all in parallel. So in essence, this main flip-flop maintains the original functionality of the design, and the S flip-flop is the one we use to see when we are at critical levels of performance and power. So in here, we have used this technology with this neural network from Xilinx. In this picture, we see 4 processing units in parallel. And in here, we see our elongate control unit that is controlling the frequency and the clock phases. We also control clock phases because not all the critical paths end up in flip-flops. Some of them end up in memory, some of them end up in DSP blocks. So we use, in that case, the clock phase to adjust timings. And we instrument only one of the DPUs, so the rest will be slaves. And this one will be communicating with the control unit. All these instrumented flip-flops will be sending information about how the system is working. When we reach a critical point, there will be a discrepancy between the slows and the main flip-flops that will be detected by this unit. And then we will have reached a critical point in terms of voltage and frequency. In here, the ARM will be setting different voltages, and the FPGA will be adapting itself to support the maximum frequency it can for that voltage that has been given. So if the voltage is higher, it will be able to reach a higher frequency, and if not, a lower frequency. And of course, all these cores are here working with the same voltage and frequency, but the ARM itself has a different power domain, so it's working in a different voltage and frequency itself. So of course, once we add these detectors, we have some overheads. So it's always interesting to see how big are the overheads. And here, of course, it depends how much protection you want. Once you start adding these instrumented flip-flops, and you are instrumented the critical paths, there could be very large number of paths. Some are more critical, some are less. So in essence, the designer has some controls that will say what sort of percentage of the paths he wants to protect. And the more you protect, the bigger overhead you have. In this figure, basically what we end up normally setting is for around a 5% overhead. That means that about 10%, or in this case, around 12% of our paths are being protected. And we've seen experimentally that this sort of protection makes the system work in a solid way and not find errors that are not detectable and cause problems. So what happens when we deploy this? Here we see the power scalability on this sync ultra scale. What we see is that the nominal voltage in this device is 0.85 volts. It's a 60 nanometer device, but we can drop voltage down to 0.55 and still maintain correct functionality. And here we see the different levels of scalability of the neural network for different voltage levels. So in blue, we have the original 0.85 volts. And we can see that the frequencies ranges from 210 to 300 and almost 400 megahertz. So that's also when we add this instrumentation, not only we can drop voltages, but we can increase frequencies. So we have like an elastic system where we can move through many different levels of power and performance. Then as we drop to 0.75, we have a new line, and down to 0.55, a new line. So what we can see overall is that we can drop power up to 85% by using this approach, or we can increase performance by a factor of 2. And of course, if you want to maintain performance constant, the power will be reduced by around 50%. So in here, the idea will be changing between different operands of frequency and voltage to obtain this concept of just delivering the performance you need for the job you have. So if the job is more complex, you run faster. If it's less complex, you run slower. What happens when we deploy these techniques? Also, a typical question is, well, what happens if you exceed the operating points? Does the system just hangs? Actually, interestingly, in this neural network, we've seen that there is still a margin of time where we see discrepancies in the output. So we cannot guarantee anymore that the output is the same as before, but the overall accuracy does remain constant. It's almost like the neural network has some built-in tolerance that although some of the critical paths are failing and some arithmetic operations are not completing correctly, the overall performance is being maintained. The overall accuracy, as you can see in here, from the point the detectors find the first errors, it stays constant until we reach a point where basically, yes, accuracy degrades quickly as we we just run too fast for what the silicon can do for us.
Jose, just let you know we have a few minutes, okay?
Yeah, yes, I'm reaching now conclusions and future work. So what we see here, well, with FPGAs, the advantage we have is that we can have custom circuits where we can have many different levels of precision, ranging from a single bit for weights and activations to floating points. The DPUs at the moment are specialized for 8 bits, but there are different versions where you can drop precision down to 1 bit, and that gives you an interesting range of complexities, performance, and so on you can play with. Also, we see how adding this instrumentation, we can get more out of the silicon than the worst case. So we are operating, the system will adapt to the environment and will deliver performance depending on the sort of variability, the sort of environment is working under. We also see that by combining different technologies like HTPUs and FPGAs, we can obtain scalability and we can make them both work at different precisions and train them only once. We can customize, we can do a single training step and then customize it for different pieces of hardware and make them work in parallel in a more optimal way. So future work is, exploring further how we can combine things that are not just DPUs, but things like neural compute from Intel or other sort of heterogeneous devices, and how we can implement this energy proportionality in a practical way, how we can understand the complexity of the, for example, a video frame and adjust the performance depending on that. So here are more details if you are interested in this kind of thing. And just thank you to the Royal Society and Silence for the support. So thank you.
Jose, thanks very much. So some interesting considerations there about acceleration in dedicated hardware and use of FPGAs. And again, interesting observations with regard to the software and how you do the integration in that regard as well. Our final speaker is Matt Holdsworth from Lattice Semiconductor. Now, we tried to persuade Matt to do this presentation live while looking after a 2- and 5-year-old, and he probably wisely decided to pre-record the video. But Matt is online, so whilst we're playing a video, which will kick off now, do be aware that if you want to send in questions, he's actually online and we'll be able to answer and will join us for the Q&A. So over to the virtual map now.
Maybe give me a thumbs up if you're happy for me to start. Okay, good. Hi, so yeah, my name is Matt Holdsworth. I'm the local FAE for Lattice Semiconductors working in the UK. So today I'm going to be covering one of our AI-based products, our Sense AI solution, talking about how we make it easy for you to get implement AI on a small, low-power edge AI device. So a little bit of scene setting first. I don't have many marketing slides. In fact, this is probably the only one. But I think it's useful to just talk about what we're trying to do here. So I've been at Lattice for a while now, probably about 13, 14 years. I've seen this slide move around quite a bit, back to the cloud, back to the edge, and so on. But certainly at the moment, the trend is very much to push more processing into the edge. So privacy concerns around GDPR and so on are definitely one of the pushes of this, but also latency, bandwidth, and actually the availability of devices with enough processing power to do meaningful processing at the edge, all meaning that it's actually very viable and very valuable to be able to do processing right at the point where the data is captured. So that's the sort of problem we're solving. Image capture, displays, anything to do with image-based AI is primarily what we're interested in. So it's quite a busy slide here, so I'm going to pause here and walk through this for a few minutes. So this is the sort of high-level overview of the Sense AI solution that we as Lattice provide. So we think of it as essentially covering all of the different components of the problem that you're trying to solve. And I actually quite like to start talking right from the very middle of the slide. So in the very center there, you can see the different AI framework tools that are available in the market. There are some others, but these are the main ones that we see and the ones we support. So you see Keras, TensorFlow, and Caffe. So these are generally where we would expect people to be doing the development of the network itself. So TensorFlow is very common. Caffe is a little, I believe there's an update to Caffe which makes it a bit more mainstream. But in any case, the development of the neural network itself, it's not something we specifically get involved in. We have some reference material to help with that, but the expectation is that the AI development would take place in one of these networks, and then you're looking for a way to take that network that you've essentially is a cloud-based or a PC-based object, and then you want to put this into something real on the edge of the network. So the first thing we provide is a software tool called Neural Network Compiler. I've got a slide showing you that a little later, but this bridges from the domain of the neural network framework like TensorFlow into our design environment. And here you can see the two tools, the Diamond and Radiant, are the main tool flows that we provide for the FPGA development side. And then the next piece of the puzzle, which is really crucial, is the RIP cores. So these are blocks of functionality we embed inside the FPGA, and they are specifically designed to process the output of the neural network compiler. So the network compiler takes your model, converts it into a series of instructions, and then those instructions are interpreted by our IP. So the IP is very optimized for the target devices. They're designed to maximize the available bandwidth and memory within inside those devices. So that's like the design environment. And then we have a series of resources that make the development a bit easier. So at the very bottom there, you can see the hardware platform. So these are evaluation kits. In the case of the one on the left, is very low cost. I think it's like $30 worth of price when you buy it at any of the distribution networks, DigiKey or any of the others available. And then on the right-hand side, this kit is slightly more expensive. I think it's a few $100s, but it has, you can see the 3-layer boards there. I've got some slide later on showing. But the idea is to provide an inexpensive way that you can get an evaluation platform into your hands and start deploying some of the reference designs that we supply. In terms of reference designs, These come in two different flavors, but what we call it a reference design is a complete suite of material. I'll go into this a little bit later on, but this is source material and data sets and so on, complete walkthrough guides that allow you to, from very little base knowledge, get a working solution implemented. And then we do have a series of design services companies, very few in Europe and not in the UK at the moment, but very actively looking to expand that network. So then, what are the typical application areas? Because the world of AI is very broad. Generally speaking, we don't cover a lot of the market, but we do focus specifically on a few target areas. Mostly those areas where convolutional neural networks can be used, and those are either image or audio-based applications. So you can see some listed up here. Object detection, very common for industrial and maybe scene monitoring and so on. Human-machine interfacing through either audio or video, very common on vending machines or coffee machines or consumer goods. And then object identification and more of a classification problem. Robots are very common. Actually, robotic vacuum cleaners, surprisingly, is or maybe not surprisingly, but we have a disproportionate number of design wins in that market. So, and we have an interesting set of problems that overlaps heavily with AI. So then back to the reference design. So I mentioned earlier we have some reference design. So there are 4 of these available. I picked out a couple here. So one is human presence detection. So this is a reference design that we provide on a low power family, our ICE40 Ultra Plus. So we're down in single-figure milliwatt processing now, and we can do a handful of frames a second. Typically for human detection, a few frames a second is more than enough. Humans don't move that quickly, and we provide a complete sort of front-to-back reference design here with TensorFlow material and FPGA design resources and so on. And this application, as is, has been used quite widely in a lot of like smart doorbells and vending machine and so on. So the aim is to provide something that you can use as is, or you can modify it if desired. And then slightly higher processing, we have object counting. So in this case, the object is quite often a human, but it could be actually any object. So now we're going higher resolution, so maybe up to 224 by 224. And then higher frames per second. So maybe we got 17 frames per second here on our ECP5 family. This family has been, this solution has been updated with a family we launched right at the very end of last year, actually, Crosslink NX family, the latest family. So now we can push towards 30 frames per second on VGA input. So I've got a bit more on that later on. And these resolutions are typically more than adequate for the sort of applications where you're using this sort of device. The automotive industry, for example, are pushing very high resolutions, but they're also in safety critical stuff. But when you're more interested in the monitoring or statistic gathering, data gathering, then these sort of resolutions are more than capable. So then typical sort of use cases where we would find our devices or an FPGA in general doing AI processing, and these are very much edge type architecture. So there is a standalone environment where the FPGA does all of the work, shown at the top left there. But much more common is the idea that the FPGA is accompanying an MCU or a CPU or some other existing software-based device. So in the term of post-processing, the image data is captured directly by the ASSP or processor, and then the FPGA acts as an accelerator for that device. So then, in this case, the FPGA takes the data from the processor, does some processing, and then gives it back via result. But actually, very commonly, probably the most common use case is that the FPGA acts as a preprocessor. So the FPGA interfaces to the sensors, does the processing, and then just provides the result to the processor. And the processor then just gets, it's almost oblivious to where the result has come from. It just gets either a bus-based interface or maybe even just a single GPIO toggle. But in this case, there's a number of reasons. FPGAs are great at being flexible on interfaces, so you're not tied to a particular sensor from version to version. You can use different different sensors, different architectures. You can even do different combinations of inputs. This is the most common use case for an FPGA-based solution. So then a quick walk through some of a bit more detail on the resources that we provide. So the evaluation platforms, we provide the two that I've shown here are the two main ones. The UPduino board on the left, this is a very small form factor. It's about the size of your thumb. The aim is to provide a very simple platform, low-cost platform for doing image and audio-based capture. So the sensor is pretty, pretty low resolution. I think it's 64 by 64 is the top end. But there's also an audio-based thing in there, and we use it for human detection, human identification, face identification, and key phrase. So all of these are built around this platform. And the reference designs you download from our web can be actually built and deployed on here, and you can test them in hardware. On the right-hand side, we have our embedded vision development kit. So this is actually a kit that we use for a broad range of embedded vision applications, one of which is AI, but there's also image signal processing and other image capture and distribution type solutions. So it's actually a 3-layer board, as you can see, a stack of 3 boards. The top board being the image capture. The middle board, which is where we do the AI processing, is the ECB5 board, or just about to launch our Crosslink NX board. And then we have an output board at the bottom. So you can distribute this to a display via HDMI or via Ethernet or USB, depending on what board you fit at the bottom. So these make for a very flexible set of solutions. These cover both the low power and the high end solutions that we offer. So then the neural network compiler, a little bit more detail here. So this is really a crucial tool in the solution we offer, because this tool takes as its inputs essentially the raw network that you've designed in, say, TensorFlow or Caffe. So the output of that is passed to the tool, and the first jobs it does, it gives you a view of that in terms of, here are the layers, here is the amount of memory required for that layer based on the number of filters, for example, or the number of nodes and the size of the weights and coefficients that you're using. And then in its simplest form, you can press generate on that, and it will give you a series of binary instructions that the IP will use to execute your network entirely. But one of the crucial roles performed here is how to manipulate or give some feedback on your network so that you can optimize it for the target architecture. So one of the really valuable things you can do is for any particular layer of your network, you want the memory requirement to be low enough such that it will fit entirely in the FPGA without the need for external memory. This really maximizes the throughput on the device and minimizes the need for external memory and really achieves the best utilization of the target device. So you can see the required memory column there in the tools. So you can manipulate this in the tool by adjusting the bit width of the different layers. You can also take this information, and the more common way to do it is you take, okay, I see this particular layer is very big. I can go back to my TensorFlow training. I can adjust this layer to be, for example, a lower bit width on the coefficients. Common usage is 16-bit and 8-bit fixed points. There's very little loss in going to fixed point from floating, although you tend to train in floating when developing. When you're developing for an edge-based, like real-world product, the transition to fixed point makes very little difference in terms of the real accuracy. And then interestingly, we find for some layers, particularly in the middle of the network, going from 16-bit to 8-bit also makes very little difference. You lose 1 or 2 percentage points maybe on the accuracy, but you gain a lot in terms of performance. So you can usually make up for that slight reduction in accuracy by for example, an increase in resolution on the input. So anyway, this is a neural network compiler. You can see there's a combination of analysis, modification. There's also a debug path in here where it can interface to the hardware and allow you to do in-the-loop hardware testing to try out particular permutations you're doing. So a very crucial tool in this part of the solution. So then the next step I want to show you is the reference designs, and this slide actually shows you the complete sort of use model, if you like, the software use case, the design flow. So in the top half is essentially your software-based process. So this is the neural network development itself inside one of the training networks. And then the next step, obviously, the neural network compiler. I've just shown you that. And then the output of the neural network compiler is a series of weights that will be stored somewhere on your board, typically in a bit of non-volatile memory somewhere, usually inside SPI Flash, for example. If you've got, you'll usually have a SPI Flash available for the bits FPGA anyway. And then the bottom half is the FPGA design environment. So this is, with the exception of the neural network IP, is a completely standard FPGA design flow. So the neural network IP clearly is customized for the AI applications, but otherwise this is an absolute standard FPGA design flow. And part of the design process is that inside the FPGA you would capture an image from a sensor, usually by bringing straight, for example, in parallel video into the FPGA. You would also then take input from so the IP has a simple instruction FIFO, and there's a couple of bits on there. One says almost empty or almost full. If it says almost empty, you fetch some instructions from the place store in the neural network compiler output, and just feed them into the FIFO until it says almost full, for example. And then by doing that, the role of the FPGA design is one of simply of capturing the input, feeding it into the IP, capturing the instructions, feeding it into the IP, and then waiting for the output some milliseconds later. So we provide, in the full reference designs, we provide all of this as source code. So we provide the training data set, the training scripts, the models itself. We provide the FPGA design code. We provide complete walkthroughs in terms of PDF guides, quick start guides, user guides, with as much as possible step-by-step process. Certainly it was step-by-step when we developed it, but if you're working on Linux, for example, there might be some system-to-system variation, but the reference design documentation is aimed to give you a complete walkthrough from beginning to end of developing this, deploying it onto hardware, running it in hardware, and seeing it work. So the idea is to make it as simple as possible for you to get to a known good working point. And then you can obviously, the licensing model allows you to modify that as needed, and you can move forward from there. So a couple of other things to point out. Our latest device, Crosslink NX, has a much higher processing capacity compared to the previous generation, ETB5, so we can double the amount of processing power. This allows us, for example, to increase the resolution or to do a quicker frame rate. But we also, at the same time, just because by nature of how the device is architected, we can reduce the power as well. We reduce the power by half. So we can double the processing, reduce the power by half. So you can see this offers a very compelling new data point, if you like, on how much processing we can do. So 30 frames per second of VGA is the target. We're very confident we're going to get, within a few frames per second of that, and the development team are looking at ways that they can achieve the 30 frames per second VGA. I believe that's scheduled for sometime by the end of the year, that level of support. So to give you a quick summary overview of what we would have talked about here, we have Crosslink NX device, the latest device, will provide the highest performance that we offer in here. What I haven't really talked about too much is the detail on the neural network support itself. So generally speaking, the neural network will need to use layers implemented in our IP. So our IP supports most of the layers you use in neural network, convolutional neural networks, such as convolution, batch normalization, and pooling, and so on. We also added support for the one-by-one depth-wise convolution for MobileNet, and some of the other layer types of the newer model types that are used. Then we also have the very low power implementation through the ICE40, down at genuine single-figure milliwatt processing. And then also the suite of reference designs that I've alluded to so far. And I have a bit more detail here on where you can find them. So on our website, if you go to the applications section at the top, just hover over that and then click on either one of these AI machine learning buttons. this takes you into a list of the available solutions. So demos are generally provided as bit streams, so useful to see the solution working, but the reference designs are the ones that are really designed, intended for use for design purposes. So we provide, as you can see here, all the complete suite of source code. So you go into the section website, click on one of those, and you'll be a page where you can download all of that. It's quite a large download, as you can imagine, but there you go. And that's it. That's the complete solution in a 20-minute walkthrough. It's quite a quick walkthrough. Appreciate that. But if you have any questions, please send them through, and we'll address them. Thank you.
Okay, thanks very much, Matt. And we have the real Matt online as well. So at this stage, I'd like to thank all our 4 speakers for some very interesting presentations, and also very much to keeping on time. We've gone through material where we've seen about memristor neuromorphic hardware. So it's really state of the art in terms of what we're trying to do with AI that offers amazing performance perspective from a power and implementation viewpoint. We've then gone through and seen an application of the technology in a challenging environment where the embedded application needs to be able to have low power. And again, we've seen sort of GPU technology used in that. We've then heard from Jose, who's really talked about the adaptive efficient computing on the FPGA side of things. And that's really been backed up by Matt, who's given us an idea for Robotics, who very much have a low power focus. So at this stage, I would normally say, can all the panelists come up and join me on stage? So literally they're getting up and virtually walking the stage, but obviously they're on video link. And really what we now want to do is have a Q&A session. And I would strongly encourage you to come on and add to that, because the danger is I have loads of questions, and if I don't get questions, I'll just ask my own questions, but you don't really want that. So I'd encourage you to use that. And as I say, if there's specific questions, come back. And I know that Ian and Matt in particular and Jose have been busy with answering questions there. I was going to start off just, I think we'll come and ask verification. So Nigel and myself are going to try and share this. We've obviously seen a lot of different platforms. People have talked about FPGAs. You've talked about specific technologies from Southampton. You've talked about GPU. Do people want to comment on where they see, is there one technology dominating here? Or is it a case of you use the technology that best suits the application you're looking at? So to any of the 4 application presenters who want to take that up.
Well, I can start, maybe get a different answer from the others, because the other talks are often focusing on non-GPU hardware. I mentioned we use GPUs quite a lot. I'd say for us, definitely we evaluate different technology and use what's best suited. Some of the other stuff that's commercially available that's been mentioned, I know we have sitting on benches in labs because we're looking at it. That said, it's not just, I mean, one of the points I was trying to make, from a business perspective, it's the wider problem. It's not just the specific embedded use case. So for us, there's a real advantage to a solution that lets us run, say, the same model in the data center as we can run at the edge. That is an advantage, especially when you consider it's a rapidly changing space, and vice versa. You know, what we can only run in the data center today, for sure, we'll be able to run at the edge in a year's time, in 6 months' time, whatever. So for us, it's yeah, the thing that is best suited to the application, but it's that includes how do you develop that application, what the future roadmap might be for where that intelligence needs to happen.
So it's still very much the standard problems of what's the software flow like, what's the power consumption of the technology, etc. And there's not really any technology you see that's thinking, oh, they're probably the leader in terms of the AI embedded space.
Well, for me, I would say the leader is what NVIDIA is doing, but that's because of their supporting infrastructure, not necessarily because of their particular power efficiency or whatever. I'd say where things differ here is this is an area which is moving incredibly quickly compared to most other areas. Like we can do things in our robots today that we couldn't do 2 years ago. I mean, that's probably even true if I said 1 year, right? It's nearly down at the months level of the pace of change. So I think that pace of change changes the weighting in sort of technology choice.
So Matt, what do you think? Obviously, I don't think you're going to agree with the GPU choice there, but have you any comments again from a technology and what the programmable companies are offering in that regard? Do we have Matt online? Okay, what about Jose or Themis? Have you any comments?
Yeah, I was about to say that obviously we see immediate benefits from using existing commercially available, hardware technologies and using them, like doing a match to the needs of the applications in terms of embedding AI and delivering this immediately. There is, however, certain applications that simply cannot be supported with the current technologies. And I just mentioned one in terms of the electrophysiology and the in vivo bioelectronic medicines applications, where the constraints are quite, harsh in a way from what we need in terms of power efficiency and computation efficiency. So I say that although, and that's perhaps a niche that we're taking with these more exotic, let's say for now, memoristic technologies that, start to emerge because you can address those particular needs. But as these technologies become mainstream, and we're already seeing products out there, for example, Intel are using these memory technologies for the 3DX point server solutions. I would say that every little helps. And although these are originally targeted for really edge computing, I could see the benefits also being transferred into the servers and into the cloud.
Okay.
I also think that, GPUs, CPUs, there is a lot of things around it that make it, using it much easier. No, there is a lot of infrastructure that you can just pick and use. While if you are working with FPGAs or maybe some other startup, you have to worry about those things. You have to create your own solution, maybe to grab data, to interface it. So the barrier into using them is much higher than you will use if you were just using something from very mature from a CPU or a GPU vendor. But what you get, I believe, is better efficiency out of that effort you have to invest.
Okay, I'm not sure if we can link her in, but Kirsten had a question. I don't know if it's possible to link her in, let her ask the question rather than me directly, but it was around verification. And I think she wanted to get an idea from a verification point of view, what really are the challenges there. Let's see if I can get the actual question.
So I believe it was originally targeted at me, but I thought it's interesting for all the other panelists as well, as applies to their particular area. So it was on what are the verification and certification requirements. I mean, it's something we think about a lot because we operate in an exceptionally safety conscious industry, and there are requirements and certifications required for everything and everybody that goes offshore. At the moment, there is not a lot out there in terms of what is required specifically for autonomy. In some respects, we are operating from my industry perspective, we're operating in a nice area. So, I mean, the example I always give is if you want to fly a drone over central London or central Bristol, you've got a whole lot of regulation and nightmare to be dealing with there. But operating and working with robots offshore has been going on for, as I said, tens of years. It's very well established. The new thing here is about making those robots smarter when they start to make decisions. And it's very much something we think about as well, because at the moment we're looking at what I think of as like collaborative or assisted AI, where you've got the human and the machine working together to make decisions, because that is the route into sort of wider acceptance of AI. But when you get to machines making decisions, these are potentially very costly decisions. I mean, it's easy to get from £1 a second up to tens or thousands of pounds a second, depending on what the robot is doing. And then it really matters, right? And you get to safety critical issues as well. So yes, there is a need for verification and certification for certain areas. I know there are some standards bodies already looking at this. Like if you look in the unmanned surface vehicle space, you have some efforts going on there. I expect we will see it in subsea case. It's something we look at. In terms of what can be done to verify autonomous systems, we have some ongoing work in this area with some partners. A company called D-Risk in Malvern, we're working with them as a joint partner on an Innovate UK funded project where we're, this addresses one of the other questions I was asked as well, actually, about making smarter autonomous underwater vehicles that can navigate closer and perform intervention tasks and close inspection tasks, which require this sort of accurate visual positioning. But then when you start doing that and you start moving your robots close to the asset, you require assurances that they're not going to crash into them and things like this. So short answer, yes, it's something we're thinking about. Slightly longer answer, we can deploy even without it in some cases. Yeah. I don't know if everyone else would like to speak about this or verification challenges with respect to their problems.
I think we've Matt online, so we haven't heard from you, Matt. So I think it's also probably the verification in that you're putting in AI functionality. If we were simply building a processor, we would verify that functionality for that processor architecture. So I think it's the ability to be able to get the AI. I think Matt's having to compete here. Maybe Temis or Jose, if you want to take that up initially.
I mean, from picking up of something that I've seen also from Ian's presentation, which we also look into that, obviously from our perspective from memoristic devices, is the R&D that is happening in terms of reasoning. And I think that's particularly useful for verification purposes as well, not just for functionality. Because how would you go and interrogate such a system? You know, like as complicated as you store, you know, like multiple synaptic weights, let's say, in your ANNs. You wouldn't go and interrogate every single, you know, like synaptic weight and try to figure out what's gone wrong. You need to develop appropriate language. As I'm using, you know, like appropriate language to interrogate, let's say, my kids if they've done something wrong at school. I'm not going directly and asking them to find, you know, like a nice set of words that I would use to allow me to figure out and reason of what has happened. So there is benefits both in terms of the advanced functionalities that one can actually get from the reasoning point of view, as well as the assurance, which is also particularly useful for security and the resilience of these system implementations.
Matt, should we try again?
Yeah. Can you hear me?
Yeah, no problem.
Yeah. Okay. Good. Excellent. Actually, yeah, I was listening in to the earlier point about different technologies as well. I was trying to. You did ask me. I think for some reason my audio wasn't working at that point. So, I guess I have an interesting take on that one because obviously I'm my company. We don't really do anything in the world of data centers, training, that sort of thing. So I get a view of AI deployment, which is very much based at in the inference side, in the real world side. And in that side, I think it divides quite cleanly between whether you have a large power budget or a small power budget. So if you have a true battery operated device, then now you're almost constrained entirely by power. You know, the cost is a key thing, but actually power can quite often be the critical driver, and burning through a couple of watts worth of device IC for AI processing is probably unrealistic. And as devices are coming down, we see MCUs increasingly, but MCUs don't have too much in the way of acceleration yet. So you kind of find yourself with AI ASPs, or if in our case we have very low power FPGAs, but then there are trade-offs the other way that you have to decide what level of accuracy I'm willing to accept. And very high accuracy at very low power. This is really the cutting edge of where I think the whole market is at the moment.
So can I lead on, and it's really a point that John Goodacre's raising on the Q&A session, is do we know what that hardware acceleration is going to be, given that AI is changing so much? So it's the balance between, if you have the classic computer architecture, you can implement it possibly inefficiently, any algorithm. When we start to put dedicated hardware, what really is going to be the trade-off between deciding what's a core proper function that's parameterizable enough versus making it general enough that you can cope with future emerging AI functionality?
I guess if
you want to continue, just Matt.
Yeah. So I try and keep an eye on what the market is doing here, and there are countless startups with exotic ways of handling the processing chain. And for certain, AI is a different problem to traditional computing. So probably once it's got some longevity behind it and there's some established best practices for neural network topologies, then it will be, you know, that someone will, you know, nail it, and there'll be a great new architecture that comes around that'll be brilliant for that. So in the interim, I think we're left with various different companies kind of betting on different approaches. And, you know, I guess there are lots of different neural network architectures. So convolution is one that's particular to convolutional neural networks and a couple of others, but then you get some AI architectures which are quite different. So, I mean, my view is skewed. We heavily work in embedded vision, so convolutional neural networks for image processing is largely the view I see. But in that space, there are quite a few different ways, but it is quite dominated by FPGA and maybe some AI DSPs or particular, some companies that I've got to work with actually have got their own ASICs for this as well. So, you know, it's a very fluid market space, I think. I'm not sure I could give you a firm view on where we're even going to be in a year's time, I think.
Okay. Well, Jose, the type of stuff you're developing, are you trying to develop and use FPGA technology as a means of being future-proofing with regard to the architecture? Jose?
Myself, okay. What I think is that all the hardware is using things like systolic arrays to do fast matrix multiplication. That seems to be more or less a core component that is being used in things like the graph cores and the Google TPUs and the FPGAs. So either you do dense matrix multiplication or sparse, but you build around that. And you then try to see how you organize your processing elements, how do you communicate with them. And then it seems to be, most specializations is to be around the feed-forward convolutional neural networks, although things like recurrent neural networks that are quite interesting, the LSTMs, the long, that can somehow not just keep a memory state of what they've seen before. Those seems to be a bit harder to implement in hardware, and many vendors do not seem to support them, while others try, although there seems to be a significant performance penalty you try to use them. So it would be interesting to see if this sort of, you know, other type of architectures can play a role in future hardware as well.
Have you any comments, Thomas, or? Your audio's off at the minute.
Yeah. No, really, I don't really have much to add from what already has been mentioned on this topic. It's quite difficult also to, you know, to compare across different technologies and different needs. I mean, we heard about deep learning as well, but there are applications that actually go well beyond that, and we've known that deep learning, although it's very efficient for certain things and for general purposes, it might be quite inefficient for specific embedded type of applications. So it's a bit difficult to compare, you know, like sort of apples with oranges in a way.
Yeah. Okay. Okay.
I mean,
sorry, go ahead, Ian.
I was just going to add a very brief point, which is, yeah, there's the focus on the accelerators for the deep learning, but that's only the perception part. I mentioned 4 other things that I consider as part of AI systems. You do see some success if I consider what we do is effectively a visual SLAM system. And there are large parts of that which are very computationally intensive, but we can't execute on a GPU or other accelerator. You do see some work towards accelerating this sort of tasks. There's some recent work out of Andrew Davison's lab on using the graph core IPU to do some of their bundle adjustment. But yeah, everyone focuses on accelerating the perception piece, but once the perception piece gets solved or more commoditized, then there's still a whole bunch of other pieces there just waiting to be improved.
Well, following on again, Alex Shekelev from Newcastle's raised this, and he talks about the notion of where we have training separate from the inference. Is there sort of a focus to try and tighten these things up? And is there maybe different ways of looking at this? Anyone? I think it was initially gauged at Matt, but I think he's offline on it. But I think it's probably back to the point you've made, Ian, and it is that, you know, there's one thing of us putting in the acceleration of specific aspects of the technology, but we may want to think about how we change things. And I know when we look at a lot of AI applications, it's a case of deciding what we have as training data and what we will run on the main system. So I don't know if anybody has any views on this in terms of how we would, you know, is there any ways that we could look to make that more efficient? Or is it a case of using a different AI technology that doesn't require training? I'm thinking more, you know, deep reinforcement learning, which is trying to not kick off from that.
Well, I guess again, this depends on the type of application, right? Because there's certain things that you sort of do your training once, and then you might want to update it only infrequently in a way. But for continuously on systems in an embedded type of setting, and then rather constrained setting, ideally you want that to be happening at the same time. And then there is also the issues to consider. So happening at the same time is obviously something that could be rather challenging in the timelines that are needed, because you might want to have a really quick response, so very, very low latencies, or in other cases you might want to be learning a system that's capable of learning, you know, like over the periods of years and applying that. And being, you know, like slower in terms of responding and adjusting, because again, that's a countermeasure to malicious sort of attacks in a way, from people that you might be feeding, you know, like false data to a system. So again, I don't think there is a one size fits them all, if I understood Alex's question.
Yeah, well, I think it's just the notion that you'll do a lot of training and then you'll put something into operation. And I think it's the fact that you've spent time doing a lot of training to get it in, you can't improve it. And I think he was trying to think of different ways that you might have a more dynamic learning environment, that you wouldn't have this long training and then into the actual operation. So I think it was more gauged at that side.
I can speak a bit to this because, so this is something we definitely think about. It's early days yet, but for example, we sponsor a student doing a PhD in exactly this sort of application. He's Pierre Nicolay up at Heriot-Watt University. He's working on lifelong learning for AUV control. So the particular problem he's looking at is, can you learn a control policy to given a visual input to drive the underwater vehicle, but then have it adapt and learn online as it is in operation? So like there's definite, like the example use case for this is our AUVs are working in changing underwater environments, or the physical state of the machine may degrade. So for example, a thruster fails, a human pilot would detect that, notice that had happened, and then drive differently to compensate for it. But if the machine can learn itself, it can learn and adapt online. So there are definitely use cases out there now for approaches that can learn online and not just split the learning from the inference. The state of the art is not currently looking at how do we make that efficient. It's looking at, can we do that at all for our particular use cases? But I can see there being a lot of work there in that area in the future for sure.
Okay, I'm conscious people are dropping off, and we sort of had a formal finish point at 12, so I was just going to finish off. I think there's just one question, and I suspect I know the answer to this, but you know, do we need floating point, and possibly where do we need it? I suspect we eventually need floating point, but can we migrate that as reduced as possible and use that to reduce the power at the front end?
Yeah, I guess I did offer an answer in the chat box on this as well, is that we increasingly see it's a trade-off. Floating point processing, the devices that do that, you don't really get them down at the very low sort of milliwatt type performance or tens of milliwatts. So it's a trade-off between the accuracy that floating point gives you compared to the processing power required to calculate the result of the network. So we increasingly see that transition to fixed point offers a minimal reduction in accuracy, but a significant reduction in processing power. So then the question is, okay, with my available processing budget, can I offset that by, for example, increasing the resolution of my image, or could more frames, a higher frame rate offset the accuracy there? So yeah, we see in my view of things, and it's not the same as all the other panelists are certain, but my view of things is that increasingly fixed point at the very edge, when you're doing AI inference in a very low power sort of environment, then fixed point is almost a no-brainer, because the available resources to do floating point just consume too much power.
I think overall the message is that for training you need at least things like floating FP16, floating point 16 bit. For inference you can keep going down. You might even be able to get away with 1 bit precision weights and activations if you are very clever and do things very well.
Yeah, we actually see, we've done quite a lot of research on this area internally. We see that at the edges of the network, the first layers, the last layers, then the precision is important. But actually in the middle layers, you're right, 8-bit is almost for free. And in some cases you can go towards 1-bit, particularly in the middle layers. And, you know, you don't actually lose too much at all in terms of when you look at the overall accuracy. So yeah, it depends a lot on the application, but for certain, in the inference world, fixed point is, you know, absolutely viable.
Okay. Any sort of final thoughts anybody wants to make? We're sort of wrapping up. I don't think I'm going to entertain more questions. Any other comments that people sort of feel that want to highlight? So just ask around. Ian, any comments?
No, I think that's it.
Okay. Thomas?
All good. I'm just responding to some questions posed in the chat room. So I think we covered most of it. I believe we'll have more time in the afternoon, I guess.
Jose?
Oh, I'm all right, thank you.
Okay, and Matt?
Oh, I think that's good for me.
Okay, look, this stage, I'd like to close the session, and I'd like to thank Ian, Jose, Themis, and Matt for making the contributions and entertaining the questions, as I say, both throughout it, and as I say, they're still doing at the minute. There's been webinar recordings and the slides will be sent to you next week. And as I say, I think that will be helpful because sometimes when you're seeing it live, you've remembered things and it's great to be able to go through that and see it again. For those joining the workshop, and I hope a lot of people can do, there's a prompt login at 2 p.m. for start. And then, as I say, there's the meeting mojos, the sort of one-to-one from 3:30 to 4:30. And as I say, having seen some of the questions go through, I think there was particularly for Matt, there was a lot of Lattice specific things that I think you would definitely want to follow up on. And I know from Ian's perspective, you know, there was quite a bit of interest in terms of the questions from an application perspective. And then obviously from an implementation point of view and collaboration, Themis and Jose, I think hopefully you'll get a lot of reaction back on that. So at this stage, I'd like to, as I say, close off and again, thank Neelam and our colleagues from Innovate and also Beth for all the work they've done behind the scenes. And I will join some of you at 2 o'clock. And so thanks very much. And I hope you enjoyed the session. Bye now.
Thank you. Bye.